People always ask me about interstellar travel. They've seen the movies, they've read the science fiction, and they want to know, is it really possible? Can we build a starship and go visit Proxima Centauri or Kepler 186f or any of these exoplanets we keep discovering? And the answer is, well, the answer is no. Not in any way that makes practical sense. Not in a way that a civilization like ours could achieve. And I want to explain to you exactly why. Because this isn't about being pessimistic. This is about understanding what the laws of physics actually tell us. And once you understand the physics, you'll see that the barriers aren't engineering challenges. They're fundamental. They're written into the structure of reality itself. So let me start with the most basic problem. Distance. The nearest star to us is Proxima Centauri. It's about 4¼ light years away. Now, what does that mean? It means that light, traveling at 300,000 kilometers per second, which is the fastest thing in the universe, takes 4 years to get there. 4 years at the speed of light. The fastest spacecraft we've ever built, New Horizons, which went to Pluto, was moving at about 36,000 miles per hour. That sounds fast, right? It's incredibly fast by human standards. But at that speed, it would take about 78,000 years to reach Proxima Centauri. 78,000 years. That's longer than all of recorded human history. That's before agriculture. That's when we were still hunter-gatherers painting on cave walls. So clearly, we need to go faster, much, much faster. Let's say we want to get to Proxima Centauri in a reasonable time. Let's say 40 years. That would be within a human lifetime. To do that, we'd need to travel at about 10% the speed of light. 10% of c. That's 30,000 kilometers per second. Now here's where the physics gets serious. How do you accelerate a spacecraft to 30,000 kilometers per second? Well, there's this thing called the rocket equation. It was figured out by a Russian schoolteacher named Konstantin Tsiolkovsky back in 1897. And this equation, it's beautiful in its simplicity, but it's absolutely tyrannical in its implications. The rocket equation tells you how much fuel you need to change your velocity by a certain amount. And the key thing, the absolutely crucial thing, is that the relationship is exponential, not linear, exponential. Let me explain what that means. If you want to go twice as fast, you don't need twice as much fuel. You need exponentially more fuel, and that fuel has mass. So now you need more fuel to accelerate the fuel, and more fuel to accelerate that fuel. It's a vicious cycle. We call this the tyranny of the rocket equation. Let me give you some numbers. If you want to build a spacecraft that can reach 10% the speed of light using chemical rockets, the kind we use now, the mass ratio would be absurd. For every kilogram of payload, you would need something like 1 billion kilograms of fuel. That's not an exaggeration. That's what the math tells you. You'd need more fuel than exists on Earth, more fuel than exists in the entire solar system. Okay, so chemical rockets won't work. What about nuclear rockets? Nuclear fusion releases about 1 million times more energy per kilogram than chemical reactions. That's much better. But even with fusion, to reach 10% the speed of light, you'd still need about 1,000 kilograms of fuel for every kilogram of payload. Your spacecraft would be 99.9% fuel. And we don't even have fusion rockets yet. We haven't achieved sustained fusion here on Earth, let alone in a rocket engine. What about antimatter? Antimatter is the most efficient fuel possible in physics. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy, according to E equals mc squared. It's the ultimate fuel. But even with antimatter, the numbers are staggering. And by the way, we currently produce about 10 nanograms of antimatter per year at CERN. 10 billionths of a gram. At current production rates, it would take about 100 million years to produce 1 gram of antimatter. And you'd need tons of it. So that's problem number 1, the fuel problem. But let's imagine that somehow we solve that. Maybe we figure out how to harvest antimatter from space, or we discover some new physics that gives us a better fuel source. Let's be optimistic and say we can build a spacecraft that can accelerate to 10% the speed of light. Now we run into problem number 2, and this one is more fundamental. This one comes from Einstein, special relativity. According to special relativity, as you approach the speed of light, the energy required to accelerate further increases without limit. Why? Because the energy of a particle, or a spacecraft, isn't just 1/2 mv squared like you learned in high school. That's only approximately true for slow speeds. The correct formula involves this factor we call gamma, which is 1 divided by the square root of 1 minus v squared over c squared. Now, when v is much less than c, when you're moving slowly, gamma is approximately 1, and you get back the classical formula. But as v approaches c, something dramatic happens. The denominator approaches 0, and that means gamma approaches infinity. The energy required approaches infinity. Let me be concrete. To accelerate a 1-ton spacecraft to 90%, the speed of light requires about 10-20 joules of energy. That's about the total energy consumption of the entire United States for 2 years. For 1 ton. And that's just to get it to 90%. To get to 99% requires about 10 times more energy. To get to 99.9% requires another factor of 10. It just keeps growing. Asymptotically, as you approach c, the energy required goes to infinity, and you can never reach c. Never. If you have mass, any mass at all, you cannot reach the speed of light. It's not a technological limitation. It's a fundamental law of physics. It would require infinite energy. This is one of the central results of special relativity, and it's been tested and confirmed in particle accelerators millions of times. We accelerate particles to 99.9999% the speed of light, and we see exactly this behavior. The particles get harder and harder to accelerate as they approach c. So, even if we solve the fuel problem, we still have this relativistic barrier. We can't go faster than light. And as we approach the speed of light, the energy requirements become astronomical. But wait, you might say, what about wormholes? What about warp drives? What about bending space-time? And here's where we need to talk about general relativity. General relativity does allow for some exotic solutions. You can write down equations that describe wormholes, shortcuts through space-time. You can write down equations for something called an Alcubierre drive, which contracts space in front of you and expands it behind you, effectively allowing faster-than-light travel without violating local speed limits. These are real solutions to Einstein's equations. They're not science fiction in the sense that they're mathematically consistent, but, and this is a big but, they require something called exotic matter, matter with negative energy density. And as far as we know, exotic matter doesn't exist, at least not in the quantities required. The Casimir effect gives you a tiny amount of negative energy, but we're talking about energies per cubic meter that are absolutely minuscule. To create a traversable wormhole or a warp drive, you'd need negative energy densities comparable to the mass energy of a star. We don't know how to do that. We don't even know if it's possible. And there are theoretical reasons to think it might not be possible. Quantum field theory suggests that there are constraints on how much negative energy you can concentrate in a region. These are called quantum energy inequalities. They might make it impossible to create the exotic matter configurations you need for wormholes or warp drives. So that avenue, the general relativity loopholes, they're probably closed too. Or at least they require physics we don't understand and technologies we can't imagine. Let me talk about one more problem: cosmic rays. If you're traveling through interstellar space at a significant fraction of the speed of light, you're going to be bombarded by cosmic rays, high-energy particles zipping through space. And because of your motion, these particles will be blue-shifted. They'll hit you with even more energy than they normally have. At 10% the speed of light, a hydrogen atom in interstellar space hits your spacecraft with the energy of a high-speed bullet. At 90% the speed of light, it hits like a nuclear bomb. This isn't just bad for your electronics, this is bad for your DNA. This is bad for any biological matter. The radiation dose would be lethal in hours or days. You'd need shielding, heavy shielding. But shielding has mass. And remember the rocket equation. Every kilogram of shielding requires exponentially more fuel. It's another vicious cycle. Or you'd need some kind of magnetic deflection system, but that requires enormous amounts of power. Power you have to generate somehow. Power that requires more mass. Now, you might argue that these problems could be solved by a sufficiently advanced civilization. Maybe a civilization thousands or millions of years more advanced than us. And maybe that's true. But here's what I want you to understand. These aren't just engineering challenges. The rocket equation is fundamental. Special relativity is fundamental. These are laws of physics. A more advanced civilization might have better materials, better computers, better power sources, but they still have to obey the rocket equation. They still can't exceed the speed of light. They still need to deal with relativistic energy requirements and cosmic ray bombardment. The laws of physics don't change just because you're more advanced. Let me put it another way. Think about the Apollo program. We sent humans to the moon, 250,000 miles away. It required the largest rocket ever built, the Saturn V. It cost hundreds of billions of dollars in today's money. It required the focused effort of an entire nation at the height of its technological power, and the moon is right here. It's in our cosmic backyard. It's 1.3 light seconds away. Proxima Centauri is 4.25 light years away. That's 100 million times farther. And the difficulty doesn't scale linearly. It scales exponentially due to the rocket equation. And we haven't even gotten to the nearest star yet. There are 400 billion stars in our galaxy, and most of them are thousands of light years away. This is why I think the Fermi paradox, the question of where are all the aliens, might have a simple answer. Interstellar travel is just too hard. The universe is full of life, maybe, but that life is stuck in their solar systems by the same laws of physics that bind us. The distances are too vast, the energy requirements too severe, the barriers too fundamental. Now, does this mean we should give up on space exploration? Absolutely not. There's plenty to explore right here in our solar system. Mars, Europa, Titan, the asteroids, these are all accessible with current or near-future technology. We can build colonies, we can terraform planets, we can spread throughout the solar system. There's work for thousands of years right here. And who knows, maybe we'll discover new physics. Maybe there's something beyond the standard model that opens up new possibilities. Maybe there are loopholes we haven't thought of. Science is always surprising us, but based on what we know now, based on our current understanding of physics, interstellar travel looks impossible. Not improbable, not just difficult, impossible in any practical sense. And you know what? That's okay. Understanding the limits of what's possible is just as important as dreaming about what might be. The laws of physics aren't obstacles to be overcome through optimism or determination. They're fundamental truths about reality. And respecting those truths, understanding those truths, that's what physics is about. That's what I wanted to tell you today. The physics that makes interstellar travel impossible. It's not what people want to hear, but it's what the equations tell us. And in physics, we follow the math wherever it leads us, even if we don't like the destination. Thank you for listening.